We've described so far the contact mode of operation of the AFM, in which the probe is moved towards the surface until some constant desired deflection is achieved, and then scanned over it, maintaining that deflection. That's shown in panel 1. Early on in the history of AFM, non-contact mode was introduced by a group at IBM Zurich. And the idea here was, first of all, of course, to interact less with the surface, but also to achieve a particularly sensitive form of detection. Because if you remember, when we talked about the response of a cantilever as a function of frequency, so here's the resonance of the cantilever, I pointed out that at low frequency there was always this contribution of very large noise, so-called 1/f noise, which comes from the weak mechanical components in the circuit. The smaller the spring retaining something in place, the larger its amplitude of motion under thermal driving, and therefore for contact mode, which operates around zero frequency, it's a static deflection, the 1/f noise contribution is substantial. If the detection scheme can be moved up to some finite frequency, some bandwidth around a finite frequency, the noise can be reduced substantially. So in non-contact microscopy, the probe is oscillated up and down at some amplitude A far from the surface. When the probe is brought closer to the surface, the amplitude changes because of long-range interactions between the probe and the surface, and so by making an amplitude set point that is different from the free amplitude, the probe can be operated in non-contact mode. I'll talk about this more in another slide. So the problem with this is that if in fact the probe should accidentally contact the surface because of roughness, rapid changes in height of the surface, it will stick to it with an adhesion force that can be very large, and then no amount of oscillation of the probe will pull it off the surface again. A solution to this is shown in 3, which is intermittent contact or tapping mode. In intermittent contact or tapping mode, let's plot down now the force versus distance for the probe. It's looking like this. In intermittent contact mode, one oscillates with such a large amplitude that when the probe hits the surface, so here is a oscillation versus time, hit the surface, and I'll just show that oscillation flattened out because of hitting the surface, the deflection of the probe from the equilibrium point delta z is so large that k delta z is much greater than any adhesion force. The result is that then on the downswing, the probe will simply be pulled out of adhesion. This technique has the advantage that it is unconditionally stable, and also that the signal is at a frequency away from zero, so the 1/f noise problem is dealt with. It's true that one hammers the surface in this mode, but funnily enough, it's better to hammer a soft sample on the surface than it is to push it sideways, because often something soft is held to the surface by rather weak shear forces. So let's turn to the implementation of these various modes. Schematic A is essentially the same as the schematic I showed you for the scanning tunneling microscope, except now the input to the servo system is the cantilever deflection signal, and the output of the servo drives the height of the AFM probe above the sample. Schematic B shows how AC mode or dynamic force microscopy, be it non-contact mode or tapping or intermittent contact mode, works. So in this case, one adds to the Z piezo a high-frequency oscillating signal that drives the cantilever into oscillation like this. And so one picks up in the detector the AC component of the signal, like this. So this is now just purely an AC signal. and then puts it into a circuit that either is sensitive to the root mean square amplitude, or alternately and preferentially is a genuine lock-in or phase-sensitive detector, so that with an AC signal in here, one gets a DC signal that is proportional to the oscillation amplitude of the signal, and then this is fed back into the height of the cantilever so as to maintain the amplitude of operation at the desired set point. The next panel, panel C, illustrates a very important mode, frequency modulation, AFM. This mode works as follows. The cantilever has a resonant frequency which depends on the spring constant of the cantilever and its mass, but also, when it is close to the surface, on the interaction forces between the cantilever and the surface, and I will represent these by a spring K tip surface. So the resonant frequency of the tip changes when the tip approaches the surface, function of K, T, S, and M. And so by setting the tip into oscillation, by providing positive feedback in the servo loop, and then measuring the frequency of resonance and adjusting the height so as to hold it at some desired frequency, an image can be made of the surface again. The reason for the extraordinary sensitivity of this mode is as follows. In detecting an amplitude of oscillation, one can make this measurement to perhaps a few percent. However, frequency measurements can be made to almost arbitrary accuracy, to a very small fraction of a hertz. So if a probe can be operated at megahertz, as is possible in ultra-high vacuum, and by dwelling over a point on the surface for a long enough time, the frequency measured to a tiny fraction of a hertz, one can achieve enormous sensitivity and thus very high height resolution. Finally, panel D illustrates how one switches between contact and non-contact mode in dynamic force microscopy. So I'm going to turn the force curve there on its side. It's shown this way in the panel because that is in effect what one sees on approaching the surface. So here is this force versus distance curve. In tapping mode, one is operating over this range of amplitudes with the probe equilibrium position being here somewhere. In non-contact mode, one keeps the probe far enough away from the surface and the amplitude small enough that one never goes into this region here where the probe will spring into contact. How does one do this? Well, remember I told you that the resonant frequency of the cantilever was a function of the effective spring between the cantilever and the surface. If the force is attractive, it means that on the downswing of the probe, it's pulled to the surface more than it would be. The amplitude is effectively increased by these tip-sample interaction forces. This is equivalent to decreasing the stiffness of the spring, and therefore, if one plots the resonance curve of the probe as a function of frequency, a free resonance that might look like this is lowered when the probe comes towards the surface like this. So by operating above the resonant frequency, a drop in amplitude will correspond to proximity to the surface. Now in tapping mode, one sees a drop in amplitude also, but for completely different reasons. In that case, the drop in amplitude occurs because the cantilever is pushed up hard against the surface, thus reducing the oscillation amplitude of the cantilever.